Morning, guys.
Morning, guys. Mrs. G here.
And Mr. Kane here. So we're going to combine the gas laws today, huh?
I'll bet this is going to be tough. Let's see, 4 gas laws, and this part's called combined.
So we're going to combine them.
I'm going to combine them, yep.
So does that mean that we're going to get out our combine and we're going to till them up?
Yes.
Okay.
We're going to smoosh them all together.
Smoosh them all together. All right. So before we can smoosh them all together, we got to talk about this thing called STP.
Okay, a little side trip here. What is STP, Mr. Kane?
Well, it's the Stone Temple Pilots.
Oh, is that what it is?
Yeah.
I thought it was the stuff you put in cars.
Oh, yeah, it's that oil treatment, right? Actually, no, STP in chemistry isn't either one of those. It turns out it stands for standard temperature and pressure.
Ah, so numerical values for temperature and pressure.
Yeah, because we have to have a standard, right?
Right.
Okay, so the standard turns out to be a pressure of exactly 1 atmosphere, which makes it easy to memorize.
Yep, that's easy. That's
Right.
what we're sitting in, basically.
Now, if you want to memorize different things, you know, it could be 14.7 psi, 101.325 kilopascal, 764 or 750 millimeters of mercury.
Stop.
Yeah, we don't need to do that, do we?
Nope.
Those are conversions.
We can
the same
convert
thing.
1
Yeah.
atmosphere.
All right. The standard temperature is
0 degrees Celsius, which would be 273 Kelvin. So anytime a problem says STP,
you're assuming.
that's the pressure you write down and the temperature you write down.
All right, so putting them together, here's the magical formula. I can actually see several gas laws. Here's PV equals PV, right?
Boils.
That's Boyle. I could see pressure over temperature.
That's Lusak's.
Charles is volume over temperature,
Yeah,
right?
yeah.
And then there's a volume over number of moles.
Which was Avogadro's.
Which was Avogadro's. So all of the gas laws are here. We're not going to show the algebra on how to get this. We just have to trust that the combined gas law works.
Yeah.
Right? So for realistic situations where more than 2 things are changing at a time, we've got P1V1 over N1T1 equals P2V2 over N2T2.
So we have to just make sure that the variables given to us in the problem gets put into the right spots.
Exactly. And that they're in matching units.
Yes, they don't have to be in specific units except for temperature, but they do have to algebraically cancel.
Right. So if one unit of pressure is in atmospheres, the other one's got to be in atmospheres also.
Right, because otherwise if one's in atmospheres, one's in millimeters of mercury, you can't do the math. It doesn't work.
Right, because the units won't cancel.
Now that's a big whopping algebra problem, but as long as you put things in the right spot, you're okay.
Mm-hmm.
Oh, that's interesting. Well, yeah, that would make sense, yeah.
And another item, if they don't mention that a variable changes, you can just remove it from the equation. So if they don't talk about number of moles in the problem, then we assume number of moles is the same.
Same value, yeah.
Same value twice. But basically, mathematically, what you're doing by crossing it out is you're just saying, hey, they're both exactly the same. So
Right.
let's say that, you know, it's 1, because 1 is not going to affect the problem.
Now, well, 1 divided by 1, it's going to come out in the wash anyway when you do the math.
And 1 times 1 is this.
Ooh, look at that. An example. Ooh, look at that. An example.
A balloon is filled with 1.5 moles of nitrogen gas to a volume of 700 milliliters, if I read that right,
Correct.
at a temperature of 20 degrees Celsius and a pressure of 1 atmosphere. The balloon is then cooled to a temperature of 1 times 10 to the second Kelvin and a pressure of 12.0 psi. What is the final volume of the balloon? Okay, well, I'm looking at this, Mrs. G, and I see that I've got 2 different units here. I've got atmosphere and psi. I don't need a calculator to convert the atmospheres to psi.
No, 14.7.
14.7. I'm checking out my temperatures. They're also different.
All right, do me a favor, Mr. Kane. Let's go through.
Okay, so you want me to list the variables?
Yeah, let's do that.
P1, V1,
T1, N1.
N1, T1, right?
All right.
P2, V2, N2, T2. Okay, so this is kind of the guess method again, huh?
Yeah. So I see 1.5 moles.
So that's a number of moles, and that sounds like a starting number of moles.
And I really don't care that it's nitrogen gas because it gives it to me in moles. I don't have to mess with molar mass or nothing like that.
Okay.
Right? So, I mean, it could really be any gas, but... All right, so then to a volume of 700 mils, so volume is 700 mils.
All right, I'm going to write that in regular notation rather than
All
scientific.
right. Temperature of 20. Now, any gas law has to be in Kelvin. That's 293.2 kelvins.
All right,
With sig fig rules.
3.2 Kelvin with sig fig rules.
Right, with the correct sig fig rules for adding. and a pressure of 1 atmosphere. So all that first line is our first set of conditions, which we are going to number as the 1, set of conditions number 1. All right. The balloon is then cooled to a temperature of 100 Kelvin. So there's temperature number 2, and a pressure of 12 psi. Okay, so we got to do a little work here, a little legwork. We're going to have to change pressure number 1 to psi. Is that the easiest way?
Like I said earlier, like we both said earlier, it sounds like that's easiest to convert because 1 atmosphere is 14.7 psi.
Let's see. What is final volume of balloon? So our volume is our unknown. They say nothing about adding more quantity of gas. That means the number of moles is constant. They don't change that. So
we
it's
get
also
1.5
moles.
right?
Yep. All right.
Okay. So here we go. P1V1 over N1T1 equals P2V2 over N2T2.
We'll put everything in the right
Holy
spot and we're
shnikes.
good.
All right, pressure 1 is 14.7.
Uh-huh.
Volume 1 is 700.
Yep.
N1 is 1.5.
Yep.
And T1 is 293.2.
Yep.
All right. Now, pressure 2 is 12. Volume 2 is unknown, so I'm going to put a big fat V there. N2 is 1.5, and T2 is 100 Kelvin. All right, Mrs. G, I got that done.
I get 293 milliliters for the volume 2.
For V2.
Yep.
All right, so volume is 293 milliliters.
Mathematically, algebraically, what I did was kind of a zigzag. I multiplied 14.7 by 700 times 1.5 times 100, and then divided it by the product of 12 times 1.5 times 293.
You did cross multiplication.
Yeah, I did cross multiplication. All right, cool. All right, another one. Can we do the same routine, Mr. Kane?
I think so, probably. All right, P1V1 N1 T1. P2 V2 N2 T2 because we're dealing with a combined gas law problem.
And we're dealing with 2 sets of conditions. So they've got a sample of gas at a certain temperature pressure, and they go and mess with it.
Okay.
All right, let's see. Neon gas. So temperature 25 degrees Celsius, that's plus 273. It's going to be 298.2.
Okay. Kelvin.
Has a volume of 1.51 liters.
1.51 liters.
And a pressure of 0.836 atmosphere.
0.836 ATMs.
All right, they don't mention N at the moment.
Okay.
Then it says calculate the volume. So volume 2 is going to be my unknown.
All right.
Of the gas after it is pumped into the glass tubes of the sign, where it shows a pressure of 785 torr. Now that's got to be in atmospheres. So 785 torr is 1.03 atmospheres.
1.03 ATMs?
Yep.
All right, I showed my dimensional analysis there.
Thank you. Temperature at 250 plus 273, that's 523.2 Kelvin.
Okay, and since they don't mention number of moles, I'm just going to put a 1 for each one of them. Assume that it was 1 mole.
Yeah, it's constant, so yeah.
Pressure 1, volume 1, number 1, temperature 1, pressure 2, volume 2, number 2, temperature 2. All right, here we go.
All right, so everything in its right spot.
0.836 for pressure, volume is 1.51, divide by N1, which is 1, times T1, which is 298.2. Pressure 2 is 785. I'm still looking for volume.
Nope.
No?
You put pressure 2 in as torr, Mr. Kane. It's got to be atmospheres.
Yeah.
Same units. Not specific.
So 1.03 for
Right.
atmospheres then. And I should probably have circled that. 523.2 for Kelvin.
Put your N in. You like to use your N, so
Oops,
put 1 in.
times 1.
And you get an answer for 2.15 liters. Now, Mr. Kane, I do it just a smidge different from you. If one of the variables is held constant, I actually leave it out of the combined gas law.
Yeah, multiplying by 1 or leaving it out.
Right,
Either
it's
way,
the
it
same
doesn't do
thing.
anything.
Nice algebra.
That's it.
Well done. We're done with the combined gas law?
Yep.